Welcome to a lesson with Dr. Powell. Let's take a look at trigonometric identities that come from thinking about the unit circle in complex number terms. What is a complex number? Well, square root of -1 is equal to I, at least that's kind of what we say. At least we have this particular type of idea, which is perfectly valid if we extend our view to two dimensions. If we think of multiplication as being something where we plot something in terms of something else, which is completely natural. When we think like 2 times 3, what we're doing to the number line is we're kind of beefing it up so that every one is now 2, and then we're just plotting 3 in that to end up getting 6. Or it's like taking 3 groups of 2 where every unit is now 2 or something like that. So the same basic type of thing follows, but if we do 2 dimensions, in order to plot something in terms of something else involves a little rotation business as well. So if you have something going up away this way, if you do that and you're plotting with respect to it, it's almost like it's actually a rotation. And if you rotate, so multiplication becomes a rotation. And if you rotate twice by 90, you actually get to -1. Very natural. So I is up here. And kind of adding across and thinking about these two-dimensional numbers, we actually would write something like 1 plus I right here for this coordinate. That's a complex number. In particular, if we take a point right here on the unit circle, you take its x coordinate and you take its y coordinate. Suppose this is pi 6, then its x coordinate would be square root of 3 over 2. Its y coordinate would be 1/2, and you could represent this point as a complex number. Now, complex numbers are great for their multiplication's sake, and it really does help a lot with understanding some of the trigonometric identities. So, because they can kind of be grouped really quickly under one umbrella, 2 different types of identities that occur, either Pythagorean or complex, even from one simple idea. What if, now, multiplication by a complex number on the unit circle with the unit length of 1 here actually is always equivalent to rotation. If we multiply it by a complex number that's off here, we actually also get expansion, which we don't want. But if we're on the unit circle, any point here, multiplying by it is like a rotation. So if we multiply by a complex number here and a complex number here, the result is just to add the angles. So we get angle adding formulas by thinking about complex multiplication. For instance, let's suppose that this guy right here is cosine of theta plus I sine theta. And this one right here is maybe cosine of phi plus I times sine of phi. Okay, now what happens when we, now if we multiply these two together, we should get the coordinates that occur when you take, so yeah, when we take this, so this angle and this one, so you take this one and shift it over here. So one angle plus another one. So you get theta. So basically what you do is you get theta plus phi. So the full angle right here, we end up getting to this coordinate, which will be the same thing as cosine of theta plus phi plus I times sine of theta plus phi. And we'll get that when we simply multiply these two guys together. So if we multiply these two together, let's see kind of how that works. But let's do it with a specific, let's do this a little bit with, let's just do it the way it is here. Okay, so we get cosine phi plus I sine phi, and let's multiply it to cosine theta plus I sine theta. All right, we're going to think about a FOIL process. All right, so think, now FOIL means it kind of is code for what we're grouping together or as we're distributing. So that the O is for like the outside, I stands for the inside, and L stands for the last. Now, if we're interested to know what cosine of theta plus phi is, that's the real part, something that doesn't have any I in it. Notice I times I is -1, so that doesn't have any I in it. The L is in good shape, and the F is in good shape. The F and the L, but then you remember the F and the L together will give you the full, will give you this right here, and you'll have an identity. Very nice identity, very useful. Now the OI, the O and the I, it would give you something complex with an I in it. So it'd be the imaginary part that would give you the sign. So that comes from the OI of this multiplication. So right here, what is this? Cosine of theta plus phi? Well, that would simply be the full. So cosine of phi, cosine of theta, that's F, and then we add L to it. Now, L is I sine phi times I times sine theta, and I times I is -1, so we actually get negative sine, so we end up getting, negative sine phi sine theta. So we get an identity. This right here is equal to the cosine of theta plus phi. Now, for the OI part, we simply get O and I, and notice that we just want the coefficient. Since this is the coefficient of I, we just want the coefficient of I here as well. So we can kind of ignore the I's and just do it. So it's cosine phi times sine theta. And then we have plus sine phi cosine theta. And this right here is equal to sine of theta plus phi. Okay, so we have our two identities. For addition, we get this one. Notice what this is. This is basically cosine of angle, cosine times the other, cosine of the other angle. And then that's minus the sines of the angles multiplied together. This one is you just switch it up, cosine, sine, cosine, and sine and cosine, but you're just switching which angle goes into which one, and you add them. Here, this is subtract. Just kind of remembering these basic ideas. These are very extremely useful formulas, and all the other formulas and identities that we have actually come from these two. Thanks for watching.